And that's what we're going to get into today, is we're going to discuss how to break this down into the equivalent circuit so we can get the total resistance. So we'll start with this one. We'll give some values to this particular circuit here. So let's say that R1, let's say it's 100 ohms. And R2, we're going to say is 270 ohms. And R3 is 120 ohms. So how do we get a total resistance when we have series and parallel, but there's two different equations? So what we're going to do is we're going to break this apart and we're going to look. Earlier we had said that there was series through this one and then branched out through here. If I look at this individual part of the circuit, that looks just like a parallel circuit. So if I look at just this piece right here, in between these two resistors, the only thing that you can, only way path can travel is just between these two. There's nothing else. So this is a simple parallel circuit. So what we're going to do is we're going to create the total resistance in parallel of just these two resistors. So if we look at that, just this part right here, let's pull it out of the equation. We're going to call this, just for the sake of it, node A and node B. So we look at just between A and B. Now this would be more simplified. This is just two resistors in parallel. We would use the total resistance for a parallel circuit, and this one becomes a lot easier. So we're going to say 270 ohms in parallel with 120 ohms. We would simply plug this in to 1 over the resistor 1 plus 1 over resistor 2 and the reciprocal of that. So it's going to look like 1 over 270 plus 1 over 120. And we're going to get the total resistance of that. We're going to get a total equivalent resistance of 83 ohms. So if I take the total resistance of this and I make it into one simple resistor, that would have the equivalent of 83 ohms, would be the same as this parallel circuit here. So now what we're going to do is we're going to plug this equivalent circuit into this part right here. So we're going to redraw that. I'm getting a little bit messy here. And then where this parallel circuit was, we're going to add our new equivalent resistor of 83 ohms. So we're going to say 83 ohms here, and then we're going to put the 100 ohms there. So from a meter standpoint, from current flow, the way it flows through these two here, the value would be exactly the same. If you were looking from point A to point B, whether it went from here to here or there to there, it would still read 83 ohms of resistance. Now what we have is a simple series circuit of 183 in series with one another. So we simply use the series circuit total resistance. So in this case is RT equals R1 plus R2. R1 is 100 and R2 is 83. So the total resistance of this circuit would be 183 ohms. So this is the total resistance of this circuit with one resistor in series with two in parallel. make sure we can see it. So now let's look at this one here. So let's give some values to this one. Let's say we have 22, 10, 33, and 44. We're just going to pick those random values just for the sake of this. So we notice that this branch, if we just look at this little piece right here, that's a series circuit. If we look at just this piece right here, that's series. And these two series circuits are in parallel with one another. So if we just look at this portion here, let's call this node A, call this node B. We look at this, this is just a simple series circuit of 22 and 10. So if we look at the series total resistance formula, just the R1 plus R2 is the total. We would add 22 plus 10, and we would get a total equivalent resistance of this branch from node A to node B as being 22 plus 10, or 32 ohms. If we do the same thing on the other side, this is a purely series section. We're going to call that between node C and node D. We do the same thing. I think I'm out of the camera's lens. Let's put it right here. We'll redraw A real fast. It's 22, 10. This is between A and B, and we got an equivalent of 32 ohms. And if we do between C and D, now we've got 33 plus 44. So RT of the series is going to be R1 plus R2. In this case, 33 plus 44. A total of 77 ohms of equivalent resistance. So I could redraw these two as simply a resistor in each one, a single resistor of 32, and a single resistor of 77. And then if we put that back into our circuit, these are connected together. And now I have a basic parallel circuit. So now I have 32 ohms and 77 ohms in parallel. So I would just say RT equals 1 over the reciprocal of the first resistor plus the reciprocal of the second resistor. We got 22.6 ohms is the equivalent resistance of these two in parallel. So this whole circuit right here could be treated mathematically as just saying we were running through one 22.6 ohm resistor. So this is how you break down a series parallel combination circuits, by finding the parts that are either only in series, only in parallel. So these two were only in parallel if you could get rid of everything else. So we find the equivalent of these two and then put it in series with the other one. Now we have a series circuit and we could get a total resistance. Here we had two sets of series in parallel with each other. So we found the total equivalent resistance of these two in series and these two in series, put them in parallel with one another, and then found the total resistance of the two in parallel. And this is what's known as the equivalent circuit of this right here. So that is a quick rundown of series parallel combination circuits.